Ever wondered how your voice travels over a phone call or how your text messages are sent over the internet? This journey, my friends, is all about signal transmission, an integral part of communication technology. It's like the highway that your information travels on. Now, there are two primary ways we can transmit signals: the timeless analog and the modern digital. Each has its own charm and challenges. In the next few minutes, we'll dive deeper into these two fascinating methods of signal transmission. Imagine a wave smoothly undulating over time. That's the essence of analog signal transmission. It's all about the continuous representation of data in a waveform, a signal that varies smoothly and continuously over time, mirroring the original information being transmitted. Think sound waves, voltage levels, or varying electrical currents. These signals showcase a continuous range of values, giving a faithful representation of the original information. But it's not all smooth sailing. Analog signals have a known Achilles' heel. They're susceptible to noise and interference. Any external disturbance during transmission can distort the signal and degrade the quality of the received information. Take the transmission of sound waves through traditional telephone lines as an example. The variations in air pressure caused by sound get converted into analogous electrical signals. These signals, echoing the fluctuations in sound waves, then traverse the telephone lines, aiming to reproduce the original audio at the receiving end. While analog signals are great at conveying real-world phenomena like sound, they do have their challenges, particularly in terms of noise and distortion. Now picture a series of zeros and ones representing a coded message. Welcome to digital signal transmission. This method is all about representing data using these discrete binary values. Unlike the smooth and continuous variations of analog signals, digital signals are composed of distinct levels or states. This characteristic, known as discrete representation, allows for the precise encoding and decoding of information. But that's not all. Digital signals also have an impressive immunity to noise. This means they can be transmitted over long distances without significant degradation, making them more reliable than their analog counterparts. To illustrate, let's think about how text messages are sent over the internet. The characters in your message are first encoded into binary digits, zeros and ones, using a specific encoding scheme. These digital signals are then transmitted as packets of data over the internet to be decoded back into text at the receiving end. This process faithfully reproduces your original message with remarkable accuracy. Digital signals offer a level of precision and reliability that makes them ideal for transmitting and processing data. So, analog or digital, which one is better? Well, it's not about better or worse, but about appropriateness. Analog signals with their continuous representation are excellent for transmitting real-world phenomena like sound and images. However, they're susceptible to interference. On the other hand, digital signals provide precision, reliability, and efficiency, standing strong against noise and distortion. The choice between analog and digital depends on the specific needs of the communication system. But understanding these principles can open the door to designing and implementing robust communication technologies.